Hello, I am Alex, and this is my video for homework 4. The first part of the homework requires us to compute pose in order to get to project a cube on the reference image. In order to get the intrinsic matrix, we first have to calibrate my laptop camera. Here are a couple of images I took for calibration. Next, we must compute the futures of our reference image. Here I show the reference image with the futures circled, where the bigger the circle, the bigger the size of the future is. We will use these futures to find the matches in other photos, and with these set of matches, we can compute the relative pose between the reference image and the frame where we hold up that image. Now that I have my intrinsic parameters, I can compute the pose and find the projection of 3D points onto a 2D plane by following the formula given in the homework. The equation boils down to getting a 3D point and rotating it by multiplying the point by a rotational matrix given through pose estimation and adding the translational vector. We then multiply this by our intrinsic matrix given from calibrating the camera. The result is a three-dimensional vector. To get our 2D points, we divide by the last element of the vector, which represents the z-coordinate. Here I show the cube that's projected on the reference image. To compute my point cloud, I chose this reference image on the top. On the bottom, I took different angles of the two objects. First, we must filter out any noise matches that occurs. We first begin with epipolar constraints. In order to do that, I have to compute the relative pose between the reference images and all other images. I first calculate the relative poses and store them in a JSON file. Then I compute the epipolar constraints by using the relative pose to get the essential matrix. X1 and X2 are the reference and the other image, respectively. I use a threshold of 0.01. Here are the differences, with the top being without epipolar constraints applied and the bottom with the constraints applied. The next method to filter out noisy matches is to create a feature track, which we only keep the matches that are present in at least 4 images. I do this by maintaining a dictionary indexed on the query index, which keeps track of how many images have this feature. Applying future tracking, it does refine the matches. In the red box, I highlight some noise that were removed after applying future tracking. Now that we applied all of our filters for noisy matches, the last step is to compute our point cloud. In order to do this, we need to figure out how to get the depth of each feature. We know that in order to get the depth with respect to the reference camera frame, we need to find a vector which is in the null space of M, where each column of M represents the constraint on the depth for each feature in the reference image. I show the code snippet to construct the M matrix by looping through each match and creating a column vector, MRow, which represents the rotation constraints on the depth of each feature in the reference image. M last column represents the last column in my M matrix, which is the translational constraint. Due to the noise, it will be difficult to find a vector to be in M's null space, so our goal will be to find a vector that will minimize the result of M times the depth vector. This is the same problem as finding the total least squares for a set of depths to equal 0. This can be solved using SVD and getting the right singular vector of M. Once we get the right singular vector, we can divide the vector by gamma, which is the translational scale shared by each feature. Here's the top view of the point cloud. You can see the left is the reference image. You can see the outline of the glasses from the reference image here. You can also make out the rectangular shape of the box on the right. Now when I rotate the point cloud, you can see the edges of the box and make out the sides of it. I compute an M matrix for each pair of images and get multiple depth vectors as a result. I average all the depth vectors together to get my final point cloud. The left image is my reference image for the point cloud. And that concludes my homework 4 video. Thanks!